We are recording now. I just remember. Okay, so another question is, how do we evaluate this? How do we evaluate A1? You know, how do we even make sense of this? Okay, so here's what we do. Here is the idea. Let's just come back to the picture. Again, let's try to use what we know, okay? So we don't know how to compute all of this at once because we don't have a fundamental theorem of calculus that allows to deal with this infinity over here. Now what we can do is, we can go very, very, very far away into this region, whatever you want, far away, and stop at some point and calculate that area. So I'm just gonna put here some number. Let me put here a b, but then, you know, imagine that this b is really, really, really far away. Okay, the bigger b is, what do you think is going to happen? The more tiny is the leftover area that we're not going to be considering, right? So the bigger, and then I'm going to compute the integral from 1 to b, because that's going to give me my area from 1 all the way up to b, right? The bigger b gets, what's going to happen to the computation that we're doing is getting closer and closer to the actual area that we're trying to compute. So our job is to make b go to infinity. So we know how to calculate that, okay? So we're going to approximate A1 approximated with the integral from 1 to b of 1 over x squared dx, okay? With b, of course, has to be bigger than 1. So let me just say large enough. Okay, so we're just going to calculate the integral from 1 to b. So when you calculate that integral, this is a finite interval, and my function is continuous and so on over the interval from 1 to b. So I can use fundamental theorem of calculus there. Calculate your integral. When you plug in your limits of integration, you're going to have a function of b. Every place that you have an x, you will have b now. And we're going to take the limit of that as b approaches infinity. Does that make sense? Because now what we're doing basically is we're pushing this b further and further away. And the bigger it is, the better is the approximation. Well, let's take the limit and we get the exact limit. Okay? So, and take limit as b approaches positive infinity to get A1. So our A1 here is going to be the limit as b approaches positive infinity of the integral from 1 to b of 1 over x squared dx. Okay? So basically, when you see infinity, you replace it by a letter. I'm using b because typically we say from a to b, but you can use your favorite letter. When you see the infinity, you replace it by a letter, and then you take the limit as that letter approaches infinity. That's it. Okay? And if it would have been negative infinity, it's the same idea, just that you take the limit as it goes to negative infinity. So let's do it. Now, here, of course, you need to understand that we're taking a limit, and limits may or may not exist. Okay? If this limit exists, then we say that the integral converges to that number, and we declare that the value of the integral and that area equals that number. If this limit does not exist, I'm going to write all of this down. If this limit does not exist, then we say that the integral diverges, and then that's it, because typically your area will be infinity. Okay? All right. So, let's do the example, and then I'm going to summarize what I just said. So how do we evaluate A1? Well, the idea is, calculate the integral from 1 to b, and then take the limit. And then take limit as b approaches positive infinity. Okay? All right, so let's do it. So A1 equals the integral from 1 to infinity of 1 over x squared dx. And by definition, or we're about to define that, but our idea was, okay, I'm just gonna go ahead. I don't know how to deal with infinity, but I know how to deal with a b in there. So from 1 to b, and then we just take the limit as b approaches infinity. Okay? Why do we do that? Because now here we can now use fundamental theorem of calculus. Okay? Nothing stops me from that. Okay? So let's do it. So this will be the integral from 1 to b of x to a negative 2. And then we use power rule. So that will be x to a negative 1 over negative 1 from 1 to b. So that's the limit as b approaches infinity. Okay, so when we plug in b, we're going to have negative b to a negative 1, so that's 1 over b, and then minus 1, so that would be positive 1. So basically, we get the limit. Okay, that's it. I'm just going to leave it like that. And then we calculate this limit. What happens to 1 over b, to that term, as b approaches infinity? This goes to 0, right? So this is equal to 1, right? So because in this case the limit exists and we get a number, so we would say that the integral converges and converges to 1, okay? And they will declare that the value of that area is 1. All right, questions? So basically, what this calculation just showed is that this expression 1 minus 1 over b approximates the area. So for example, here, this means that this a1 will be approximated by 1 minus 1 over b, because that's what we obtain when we calculate the integral from 1 to b of 1 over x squared, okay? Now, of course, if your b here is very small, your approximation is not good because you're missing a lot of stuff, okay? But the bigger b gets, the closer and closer is your approximation. So the bigger that b can get is approaching infinity, and therefore it's going to get closer and closer to 1. So there it is 1. Does that make sense? So that's the idea. So that's how we deal with type 1 integrals. So let me summarize this. So in general, so we define the following. So the integral from a to infinity of f of x dx. So suppose that f is continuous on the interval from a to infinity, okay? So then the integral from a to infinity of f of x dx, what we do is we go ahead and replace that infinity, we replace it by a letter. I guess I'm going to put a b here. And then we're going to take the limit as b approaches positive infinity, okay? So whenever you see this integral, that's what it means, okay? Remember, this a is actually a number that you have, okay? This is a number that you have, and you just replace the infinity by another letter. I'm putting b, but you can put r or whatever letter you want. The point is that you need to take the limit as that letter that you put approaches infinity, okay? And we're just approximating our area little by little, okay? So we define it like this, and then we say if this limit exists, we say that the improper integral converges and set the integral to that value. In other words, if the integral equals that value. Otherwise, so if the limit does not exist, we say the integral diverges. Okay, so this notion of convergence, so we're going to talk about convergence and divergence again when we discuss series, okay? Pretty soon, we'll talk about sequences and series. But you know, we say that an improper integral converges. Basically, we're just saying that this limit exists, and therefore this integral has a number. So there's an area to make sense of. When we say that it diverges, it means that this limit does not exist. Yes.
How do we tell if the limit does not exist? Is it just if there's going to be a 0 in the denominator?
No. So remember, you discussed this back in calculus 1. So a limit does not exist. If a limit doesn't exist, it could be because of several reasons. One of them is if you get infinity. If your limit is infinity, it doesn't exist. Infinity is not a number. For a limit to exist, it has to be equal to a number. Okay, so if you're taking a limit and you obtain infinity as an answer, it doesn't exist. Also, sometimes you may have a complicated limit in which you need to do side limits, right? If the side limits are different, then you know that the limit at the point does not exist. Now, in this case, we're taking limit at infinity. So when you take limits at infinity, typically you don't have to deal with side limits. But to be able to compute some of the limits you're going to get, you need to remember L'Hopital's rule. From calculus 1, do you remember L'Hopital's rule?
Just keep doing it over and over and over.
There are 7 indeterminate forms of limits. Do you remember those? No?
No.
Okay, so I'm gonna finish writing this, and then I'm gonna remind you of the indeterminate forms. I'm gonna show you quickly how to deal with them, because some of those limits, you're not gonna get too complicated limits, but you need to be prepared for anything that comes your way. So I'll explain that. There are 7 indeterminate forms that when you see them, you cannot predict what the outcome is. You need to do something, and there is a technique called L'Hopital's rule that allows you to deal with this, but only allows you to deal with 2 indeterminate forms, the 0 over 0 and the infinity over infinity case. The other 5, what we do is we do some tricks to turn them back into 0 over 0 or infinity over infinity, and then you use L'Hopital's rule. So, but I'm gonna show you those. No. L'Hopital's rule, with L'Hopital's rule you can do this, but then before you need to do some algebraic tricks. Okay? Derivative of the top, derivative of the bottom, and then evaluate. If you still get in determinate form, the L'Hopital's rule again. L'Hopital's rule just says that the limit of f over g, if this limit is of the form 0 over 0 or infinity over infinity, as x approaches a or infinity, it doesn't matter. This is the same. You can replace it by the limit of the derivatives. But this only applies when you have 0 over 0 or infinity over infinity situation. Okay? But there are 5 more. There is 0 times infinity. There is 0 to the 0, 1 to the infinity, infinity to the 0. Those cases are indeterminate forms, and you cannot use this directly. We do some tricks to turn those forms into this form, and then use L'Hopital's rule. I will show you that. I will show you that. It was in Cow 1. You did this in Cow 1. All right, so if this limit exists, we say that the improper integral converges and set the integral to a value. Otherwise, we say the integral diverges. Now, similarly, if f is continuous on the interval negative infinity, let's say to b, then if you have the integral from negative infinity to b of f of x dx, we do this in a similar way. So instead of negative infinity, we can put an a here, right, and calculate our integral, but then we need to take the limit as a approaches negative infinity. In other words, whatever letter you pick, you can use your favorite letter. You pick to replace the infinity, then you take the limit of that infinity. Okay, that's the point. And the same thing, if the limit exists, it converges and equals to a number. If the limit does not exist, it diverges. Okay? If the limit exists, the integral converges. Otherwise, it diverges. And when we say diverges, that means that the integral does not, it doesn't equal any number, okay? Many times it will go to infinity, which will have a meaning, like the area is infinity, okay? But sometimes you can just say, you cannot make sense of it, because it could be that your limit doesn't exist because of all the conditions, not just because of being infinity. Okay, we're gonna do examples, but let me just first explain the 2 types, and then we're gonna do examples. I'm gonna remind you of those techniques to calculate limits and so on, okay? All right, questions about how to deal with type 1 improper integrals? So let me just say remark. if f is continuous on the entire real line, so on the entire interval, then you could have this, the integral from negative infinity to infinity of f of x. And if you have this, if you want, you can say this is a type 1 improper integral 2 times, right? So what we do is we split this into 2 integrals because we always want to have one problem at a time, okay? We want to deal with one situation at a time. So just pick whatever is your favorite number on the real line and just split it at that point. Typically, we will pick 0, right? But you can pick whatever your number is. So I'm going to write from negative infinity to a f of x plus the integral from a to infinity f of x dx. And now this is type 1, this is type 1, and then you evaluate both of these. We typically will pick 0, but a here can be any number that you wish. Yes?
Can't you not pick 0 if it would create a type 2?
So that's why it's not going to create type 2 because of this. That's why I'm saying f is continuous, right? So I know that there's no issues, right? So I know that there are no issues. Yeah, so if you're going to create an issue, then you don't do that. So where a is any fixed real number. Again, for convenience, we typically would pick 0, but I don't want to force you to pick 0. You pick whatever you want, okay? Okay, so, and then what do we say? Okay, notice that there are now 2 integrals, right? So it could be that one of these converges and the other one doesn't, okay? So we will say that this integral from negative infinity to infinity converges if both of these converge, and then it will equal to the sum. If one of these diverge, that's it, the integral diverges, okay? So, this integral converges provided that both integrals, these ones over here, converge. Okay? All right, so that's it for type 1. We're going to do examples later. Let me talk about type 2. So let's see, type 2 improper integrals. So type 2 improper integrals. These are the integrals for which the interval of integration seems okay, so the limits are okay. It's just that the function is the one that has an issue. In these cases, our function didn't have an issue. The functions were nice. Now, the problem is with the function, type 2 improper integrals. So how do you recognize this? The function f of x is not continuous. Typically, is because it's unbounded. Unbounded on the interval AB. Okay. So, for example, our integral A2, or A2 from above, which was the integral from 0 to 1 of 1 over x squared dx. So you have to be careful because you could be tempted to go ahead and calculate this as an unusual integral, but you need to understand that 1 over x squared is not okay with 0. Okay? So note that here f of x equals 1 over x squared is not continuous at x equals 0. Okay? It is actually unbounded. When we get close to 0, it shoots to positive infinity. Okay? So it becomes unbounded as x approaches 0. Okay, so as x approaches 0, our function is going up to positive infinity. Unbounded means that it goes either up to positive infinity or down to negative infinity. Okay, so there is no number for which the function cannot go beyond. That's what it means. The value of the function grows bigger and bigger in absolute value. That's what it means to be unbounded. Okay, so how do we deal with this? Well, it's actually the same idea. We're just gonna replace the problem. So if the problem was inside the interval and not in one of the limits, what we do is we split it because we want the problem to be in one of the limits. Okay, once we have it in one of the limits, then we do the same technique. We replace it by a variable and then we take the limit, but this time as we approach that number. There's no infinity here. Okay, now you need to do it. If the problem is in the bottom, you need to understand that the interval, so let me show you what's the picture. If the problem is in the lower limit, right, the problem is here at 0, then we're gonna replace the lower limit by some letter. I'm gonna say a, and then we're gonna approach 0. But how are we approaching 0? From the right or from the left? From the right. So we need to take the limit as a approaches 0 from the right. We have to take a right limit. If the problem would have been the top limit, then you need to understand that the picture would be like this. Let's say, whatever. Let's say that this would have been a -1, for example, x squared minus 1, right? Then the problem would be a 1, right? So then we will have here some letter, let's say b, but this time we're going to approach 1. But how do we approach 1? From the left, okay? So you need to accordingly replace, take the corresponding side limit. Okay. All right, so that's what we're going to do. So in this case, so the idea, replace the limit of integration that has an issue with a variable and then take a side limit. Okay, so and again, I'm gonna formalize all of these below, but let's see the example first. So we have something like this. 0 is a problem, so I'm gonna put a variable in there, and then I'm gonna take the limit as x approaches a. How should we get close to a? From the right or from the left? Just think about the interval, right? So you want to x approaches 0. Sorry, x approaches a approaches 0. Why am I saying x? So a approaches 0 from the right, because again you have 0 is your lower limit. So this is the picture that you need to have in mind. This interval over here. You're placing your a over here, and then we're going to slowly get close to 0 and watch out what happens to the function, to the values of our interval. Okay. Okay, so let's compute. I mean, we already did the antiderivative for 1 over x squared, right? So in our previous calculation, we did that antiderivative, and it was -1 over x, right? Which is this. We're just going to use that. So, because now we can use fundamental theorem of calculus. That's a motivation. That's why we're doing this, so we can use fundamental theorem of calculus. So the limit as a approaches 0 from the right of -1 over x from a to 1. So as limit as a approaches 0 from the right of, and then when you plug in 1, you're gonna get -1, then plus 1 over a. Okay, so now we take the limit. So what happens here? What happens to 1 over a? Which one? Positive or negative infinity? Positive infinity. So this right here goes to positive infinity, and infinity minus 1 is still infinity. So this equals positive infinity. So we would say that the integral diverges. Okay. So that area is actually infinity. It's unbounded. That area over the interval from 0 to 1. Okay. Questions? Do you understand this? So, it's basically, we're bringing all the techniques that we know from integration by doing this little trick of replacing the problem with a variable, integrate, you're going to get a function in terms of that variable, and then we just take the limit. That's what we do. In the type 1, our limit is as the variable approaches infinity. In the type 2, our limit is as the variable approaches the point that gives you an issue from the corresponding side, either from the right or from the left, depending if it was the lower or the top limit. Yes?
There's no trends between type 1 or type 2 as far as like whether they converge or diverge. It's entirely dependent on the function, correct?
It depends on the function, but then we're going to study comparison theorems. In the next class, we're going to learn how to decide or investigate whether an integral is going to converge or not without having to compute it. Because sometimes an integral is very hard to calculate, and sometimes even it's impossible to calculate. But you still would like to be able to say if it's going to converge or not. So for that, we need to look at other techniques. These are the comparison theorems. We're going to discuss that. And there will be some special types, like this is what we call a P integral. And we're going to rely on these P integrals to get some results about series later on. That's why we're doing this now, because this is going to come back again in series. We're going to use some results that we're going to prove here about these guys for series later. Okay? So yeah, but the function will tell you. We're going to do some examples so you can see some calculations. All right, so let me then write down the general idea. If you see something in the chat, please let me know, because I'm typically not looking at the chat. So I don't want to leave anybody behind. Okay, so let's see. We did type 2 improper integral, so let me say in general. So in general, if f of x is unbounded, is unbounded on the interval from a to b, but continues on the open interval, the half open interval, half closed, however you want to call it, from a to b, including b, not including a. Basically, what is it I'm saying here? What am I saying here? If I say that the function is unbounded on the closed interval, but it's continuous on the half open?
Not including a.
So what I'm technically saying?
It's unbounded on A.
That the problem is at A, right? So when I want to now talk about the problem is at B, I'm going to do the same thing at the beginning, but then I'm going to put my parentheses around B to let you know that the problem is at B. Basically, I'm saying ignoring A, everything else is okay, because my function is continuous. I can do fundamental theorem of calculus, no problem. That's the reason why I need this, okay?
But if the seasons on the B, then you better look at it coming from the left.
Exactly. So from the left. And then when we put the parentheses on B, we need to take the right limit. Exactly. So if f of x is unbounded on the closed interval, but continues on the interval without A, that means the problem is at A. So in that case, the integral from A to B of f of x dx, remember the issue is at A, so this is going to be the limit as, okay, so here you have to use another letter. So as r approaches A from the right, the integral from r to b of f of x dx. So again, all we are doing is the place where the issue is, we replace that by another letter, we calculate our integral, and then we take the limit as that letter approaches the point. In this case, we're doing it from the right because A is the lower limit, so you get close to A. Okay? So my advice to you is just, have this in mind, this picture. Here is A, here is B. We're technically, placing an R in here, and then we are slowly going towards A like that. Slowly or faster, however you want to go. Okay? So that's the point. All right, and okay, let me put the other point. if f of x is unbounded, if it happens to be continuous, so if it's unbounded on AB but continues on AB with parentheses around B, this time the issue is at B, it's not at A, then the integral from A to B of f of x dx equals, so I'm gonna go ahead and replace B by R, and then I just take the limit as R approaches B, but this time I need to do it from the left, because again, think about the picture. Here is A, here is B. The issue is at B now, so we have R over here, and we are approaching B like this. So we are doing it from the left. Okay, instead of memorizing it, just do a little picture, and then it will be pretty easy to see if it was from the right or from the left, Okay, and then again, we will say that the integral exists if this limit exists, and the word that we use is converges. Otherwise, if the limit does not exist, we say it diverges. Okay, so if the limit exists, we say the integral converges. And otherwise, the integral diverges. And moreover, if it converges, the integral will equal the value of the limit. Okay, so just wanna rewrite that, but it's very similar to the one above. We okay with this? All right. So let me go to the examples then, and let's do problems so you can get the hang of this, and then I'm going to explain the limit stuff that I was talking about. So let's see examples. I'm gonna give you 5 integrals. Hopefully with those examples that will be enough. I'm gonna give you 5 integrals. First, I want you to identify the integrals. I need you to tell me the type. And then, of course, we're gonna determine convergence or divergence by evaluating. Okay? So identify the type. And if it's a regular integral, just say it's a regular integral. Okay? Because remember, in practice, you won't even know whether your integral is improper or not. You might just be given, okay, evaluate an integral. And then you need to decide whether it is a good integral or an improper integral. And if it is improper, then you have to classify type 1, type 2. Okay? Identify the type of the given integral. The given integral. Then evaluate. Okay, so let me just put them here. So the integral from -1 to 1 of 1 over x to 2 over 3. And put the integral from -infinity to infinity of 1 over 16 plus x squared. The integral from 0 to infinity of x times e to the negative x. Let's do the integral from -1 to 2 of 1 over x cubed dx. And we'll put another one here, the integral from 0 to infinity of 1 over square root of x times x plus 1 dx. Okay, so here we have 5 integrals. I want you to identify these as type 1 or type 2. So let me take attendance before I proceed any further. So go ahead and start working on this. So identify the type first, and then once you're done doing that, go ahead and try to begin computing the integrals. Okay? So remember, the way we make our definitions is, we define them in general, but when we actually talked about how to calculate them, the problem was always at the limit, right? So if you have a function, if you have an integer in which the issue is not at the limit, you need to split and put the issue in as being one of the limits. I'm talking, for example, about number 1. What's the issue with number 1? So 0 is a problem, right? But what are our limits? -1 to 1. So you will need to split this as two integers, -1 to 0 plus 0 to 1, right? And then you have to deal with those two. All right. So let's see. Number 1, what's the type? Type 2, okay. Everybody agree? What's the issue? So the issue is at 0, right? So, okay, type 2. We know where it is. Okay, number 2, what's the type? Type 1, good. Number 3, what's the type? Type 1, good. So that's the first thing that you need to do. You need to be able to identify the type of the intervals, okay? Number 4, what's the type? Type 2, good. Number 5, what is it? Type 1. Let me put it here. That's it. It's also type 2. It's an issue with 0 there, right? So number 5 is both types. It's type 1 and it's also type 2. Huh? No, because it's plus. So yeah, if it would have been minus, then yes, there would be several issues. You also have issues of 4 and -4, but it's plus. So the only issue is the infinities and the limits. Okay, so that's the first step. Why do you need to recognize the type? Because depending on the type is how you proceed to calculate the interval, right? You know that we deal with this with limits, but the limits are different. The type 1 cases, the limits are at infinity, and the type 2 cases, the limits are as you approach a number from one of the sides. Okay. Okay. So Robert Sarabia. I'm gonna say this. Okay, so let's go. So let's go ahead and let's compute these integrals. I wonder. Let's do this, and then I'm gonna explain the limit stuff with the L'Hopital rule and so on. Okay. Otherwise, I could get carried away there, and then we will do these examples. And you really are not gonna be computing too complicated limits, anyways. But you do need to know how to deal with arctangent, because as you know, many of these integrals are going to give you arctangent. For example, number 2 is going to be an arctangent integral. You need to know how to compute the limit at infinity of arctangent. Okay, so let's evaluate. So number 1, the first one is the integral from -1 to 1 of 1 over x to the 2 over 3 dx. So remember, the first thing is, we know this is type 2, but we need the problem to be in one of the limits. Right now, it's at the center of the interval. So we need to go ahead and put the problem inside, which is we need to split this. So this is the same as the integral from -1 to 0. Remember, you can always pick a point inside your interval and split your integral in 2. You can always do that, okay? In this case, we're picking 0 because that's the one that we want to pay attention of. And then the integral from 0 to 1 of this, okay? So I'm gonna go ahead and just for simplicity, I'm gonna call this one I1, and I'm gonna call this integral I2. So our integral is gonna converge provided that both of these integrals converge, and if they do, then the integral that we have equals the sum of these two integrals, okay? So let's focus on I1. So I1 is the integral from -1 to 0 of 1 over x to the 2 over 3 dx. So the problem here is at 0, right? So this would be the limit as b approaches 0, this time from the left, because the problem is in the top. From -1 to b, I'm going to write this as x to the -2 over 3, so that I can integrate immediately. So that's limit as b approaches 0 from the left, and this will be negative 2 over 3 plus 1. That's 1/3. Let's do 1 over 3 over 1 over 3, and we need to plug in from negative 1 to b. All right, so then this equals limit as b approaches 0 from the left of 3 times. So let's see, when you plug in b, we're gonna get b to the 1 over 3, and then minus 1. And then we did the limit as b approaches 0. So when b approaches 0, this part right here becomes 0, and this is gonna be equal to negative 3. Questions with this? All right, so that's this one. Let me make sure. So you do plus 1, 0, 3, that's 1, that's fine. Okay, so this one converges I1. So let's calculate I2. So then I2, yes. Am I missing a negative? So hold on. So from negative 1 to b, then that will be 3. I plug in b, then minus 1. Yes. Plus 1. Yeah, because it's minus 1. Yeah, so it's minus because of the integral, and then when you plug in the negative 1, it makes it plus. Yes. So positive 3. Good. And also, another way to have realized that is our function is positive, right? Because x to the 2 over 3, this is basically x to the 1 over 3 squared. So this quantity is always positive. So you're calculating an area here. There is no way that we can get a negative number. So we better get something positive. Good. All right. So, but we don't stop there. We need to go ahead and we have to look at the other one. Okay, I2. All right. So that would be the limit as a approaches 0 from the right this time, because we are replacing the lower limit of 1 over x to 2 over 3. We already calculated this integral, so I don't want to repeat it. So that's 3 times x to the 1 over 3. So that's the limit as a approaches 0 of 3 x to the 1 over 3 from a to 1. So, you know, once you do one of the integrals, then you don't have to redo it again. You just use the same antiderivative. So what is this? That's 3 times 1 minus a to the 1 over 3. So a approaches 0, so this one right here goes to 0, so you get 3. So both of the integrals converge. What does that mean about our original integral? It converges, and it converges to what? To 6, 3 plus 3, right? So this one right here is going to be equal to, the first one is 3, the other one is 3, so equals 6, okay? So this one right here equals 6, and then we say that it converges. Okay? Questions on that one? All right, so let's take a look at the second one. So the integral. That was a very late response, Daniel. Yeah, that's fine. I mean, at the end of the day, I'm not the one that, you know, I already know this. Okay, so again, this is a type 1 integral, but well, now we have issues on both limits, right? So our job is to make sure that the issue is just we deal with one at a time, okay? So again, I'm gonna split it. I'm gonna split it from, I'm gonna use 0. Okay. And just like before, because we have two intervals, this will be I1. I'm gonna call this one I2. Okay? I'm going to compute each of them. So I'm gonna go ahead and calculate the antiderivative first, so then we can just go straight to the limits quick. So let's go ahead and figure out the antiderivative first. Does everybody see that this is an arctangent integral? Okay, so I'm gonna factor out 16, and that would be 1 plus x squared over 16. That becomes x over 4 squared, right? Dx. So if we make u equals x over 4, then du is 1 over 4 dx. So dx is 4 du. So this is equal to 1 over 16, the integral of 1 over 1 plus u squared times 4 du. So the 4 comes out, cancel with the 16. Okay, this 4, I cancel it down here. So I get 1 over 4, and then the integral of 1 over 1 plus u squared, this is arctangent of u. This is inverse tangent of u, and u is x over 4. Okay, so that's the antiderivative, but now we need to do the limit. So let's, when you did trigonometry back in your trigonometry course, maybe you didn't see the graph of the inverse trigonometry functions, because typically the inverse sine, the inverse cosine, you don't really need to know the graph and so on, but the inverse tangent, it shows up many places. As you can see, it shows up a lot in integrals, and then if it's improper, you have to take the limit. So it's helpful to know the graph of the inverse tangent. So I'm gonna show it to you. So recall the graph of inverse tangent. So remember, this is the inverse function of the tangent function. And remember, the restriction of the tangent is quadrant 1, quadrant 4. So from negative pi over 2 to pi over 2. So that means that restriction on the x, now that will be your interval on the y. So everything is going to happen between pi over 2 and negative pi over 2 on the y-axis. And it turns out that at these points in the original tangent, what do we have? We have vertical asymptotes, right? So when you do the inverse, because x and y are switched, the stuff that are vertical, they become horizontal, right? So we're gonna have now horizontal asymptotes here and here. And then basically the inverse tangent function, it looks like the cube root function. You know, the same way that the tangent looks like the cube function between two vertical asymptotes. Now the inverse tangent looks like the cube root, but between a pair of horizontal asymptotes. Okay? So why is it helpful to remember this graph? Well, because now this tells you in particular from here, you see that the limit as x approaches positive infinity of the inverse tangent, what is this? This limit is pi over 2. And also you can see that the limit as x approaches negative infinity of the inverse tangent is negative pi over 2. So whenever you are computing a limit at infinity of the inverse tangent, you know, just remember this graph so that you can see this end behavior, okay? And we're gonna need that now. And we see, and let's see what happens. It shouldn't, because this function is positive, right? So we shouldn't get 0. This function definitely has an area. So let's see. Let's go ahead and let's compute. So I1, remember the integral I1 was the integral from negative infinity to 0 of 1 over 1 of 16, 1 over 16 plus x squared dx. So this would be the limit as b approaches negative infinity of the integral from b to 0. This is the definition. Now let's use our antiderivative, which is a quarter inverse tangent of x over 4. So 1 over 4 inverse tangent of x over 4, and then this is from b to 0. So plugging in, what do we get? So that's 1 over 4 times. Now, inverse tangent, so when you plug in 0, you get 0 over 4, that's 0. What's inverse tangent of 0? Look at the graph. 0. So that's 0 minus inverse tangent of b over 4. Okay? So what is this? So when we take the limit, so when b approaches negative infinity, b over 4 also approaches negative infinity, right? So we have the argument of inverse tangent approaching negative infinity. So inverse tangent of something approaching negative infinity, what is that equal to? According to the graph? Remember, this is the argument. So this b over 4 is like the x for the original inverse tangent function, right? So when b approaches negative infinity, b over 4 also approaches negative infinity. So you do inverse tangent of something going to negative infinity, it gets closer and closer to negative pi over 2, right? So this right here approaches to negative pi over 2. So we're gonna have 1 over 4 times 0 minus pi over 2, right? So that would be positive pi over 8. Yes? And for example, if you want to be a little bit fancy, you can say, okay, I'm just going to compute the other one, but notice that this function is even, right? So you could have done it from 0 to infinity and then times 2, the result. So we can just do, or this one and then times 2. So I know the answer is going to be pi over 4, because then the other half is just a symmetric version of this. It's just that this is happening on the left part of the, on the left part of the x-axis, and now we're about to calculate what happens to the right part of the x-axis, but it's the same situation because this function is symmetric, it's an even function. Okay, but let's just do it for completeness. So now I2 would be from 0 to infinity, and we are expecting to get the same thing, a pi over 8. So this is the limit as, oh, should have put 8, but it doesn't matter, you can use whatever letter you want. Let me just keep using b. As b approaches positive infinity, then the integral from 0 to b, this guy. All right, so that would be 1 over 4 inverse tangent of x over 4, and then from 0 to b. So what changes is that we have this at the beginning now. So inverse tangent of b over 4 minus 0, and as you know, this goes to, now, okay, what does this approaches to? So b approaches positive infinity, so b over 4 approaches positive infinity as well. And when the argument of inverse tangent approaches positive infinity, what happens? We get positive pi over 2, right? So this now equals 1 over 4 times pi over 2 as pi over 8, as expected. And so our integral is gonna equal to pi over 8 plus pi over 8, which is then pi over 4. Okay? All right, so put it here. So the integral from negative infinity to infinity of 1 over 16 plus x squared equals pi over 4, and therefore converges. Okay, questions? Do you understand? Yes? All right, so let's see, what was the next one? Integral from 0 to infinity of x e to the negative x dx. Let's see, I'm gonna give you, well, it's 1:41, so the time is gonna go by if I let you work on this on your own. Okay, so let's just do it. Okay, so this is type 1, right? So let's see, who can tell me what should I write? Tell me what to write. What do you mean by infinity from the left? Approaching infinity from the left. Can you approach infinity from the right? Okay. So remember, the side limit is only for the type 2 case, when you get close to a number. Infinity is just infinity, right? Okay, limit as a approaches infinity.
Of the integral of from 0 to a
Uh-huh.
of x e to the negative x dx.
You know, this is automatic, so you do this without thinking. That's the definition. Now, the point is, okay, go ahead, calculate this integral, plug in your limits, and you know, the limits of integration, fundamental of calculus, and then the second part of the problem is now figure out the limit that you get, right? So, but right now, let's just worry about the integral. So I'm gonna go ahead and calculate my integral here. So the integral of x e to negative x dx. Let's calculate that integral so that we can put it up there later. Okay, how do we do this? By parts. Good. So we're gonna do this by parts. What should be our u?
This is type 2 as a previous one, no?
Which one?
This one?
Number 3? That's type 1.
Sorry.
That's
And
type
then
1.
Number 2 is type 1 as well.
Yes. So what's our u here?
X.
X. And dv? E to negative x dx. Okay, good. So then du is just dx, and v is negative e to negative x, right? So we do uv minus v du. So that would be x, so negative x e to negative x minus the integral of v du, but because we have a minus, that's really a plus, and then we have this, right? Integrate, so we get negative x e to negative x minus e to negative x, because the integral of e to negative x is negative e to negative x, right? Okay, so as an antiderivative, so let's go ahead and let's plug it in here. So this is equal to the limit as a approaches infinity of negative x e to negative x minus e to the x. I mean, if you want, you can rewrite this as negative e to negative x and then 1 plus x. It's kind of nicer. And it would be more convenient. Okay, I'm gonna keep it like that just to explain something. Okay, so let me put that one here. That way I don't have to write too many e to negative x. And then from 0 to a. So that will be the limit as a approaches infinity of negative e to the negative x to the negative a times 1 plus a minus, and then when we plug in 0, okay, so as a plus because of the minus, and then we're gonna get 1 times 1 plus 0. Yes? So we plug in a, so we get minus e to the negative a times 1 plus a. That will be minus when you plug in 0. But because of the minus, that becomes plus, and then that's 1 plus 0. Very good. Okay, so this piece here is 1, so that's not really a problem. The issue is with this one. So what happens when a approaches infinity? So let's take a look at this term right here. So when a approaches infinity, the parenthesis goes to infinity, right? So this is infinity times something. What happens to e to the negative a when a approaches infinity? So think about the exponential function. How does e to the x looks like? E to the x looks like this, right? So when a approaches positive infinity, negative a approaches negative infinity. So we are really looking here. So what happens when the argument of the exponential goes to negative infinity? What does the function approaches to? It approaches to 0. So this is a 0. So this would be infinity times 0, or 0 times infinity. That's an indeterminate form. Okay? Like I mentioned, there are 7 indeterminate forms. 0 times infinity is one of them. So And how do we deal with this? Well, we need to transform this, so we will use L'Hopital's rule. In this case, it's pretty easy what to do. You see, here you have e to the negative a, but I can bring this guy down to the denominator, right? As e to the a. So we can just rewrite this as negative 1 plus a. I'm going to keep the negative in there. So, or write it as 1 minus 1 plus a over e to the a, right? You know, this is one, this part right here is 1 in the parentheses, so I just wrote the 1 in there, minus, and then this e to negative a, I brought it down here, to the positive point. So all of a sudden, now we don't have 0 times infinity. What do we have? Infinity over infinity, because when a approaches infinity, e to the a goes to infinity. Yes? So now infinity over infinity, we can use L'Hopital's rule. Or, at this point, there's really no need to use L'Hopital's rule. You can use your knowledge of the growth of functions. Exponential functions grow faster than polynomial functions, right? So at infinity, you know that e to the a is going to grow faster, therefore this is going to be 0, right? But you can use L'Hopital's rule. The derivative of the top is 1, the derivative of the bottom is still e to the a, and then you take the limit and you get 1 over infinity, which is 0, right? But you know exponentials grow faster than polynomials, so this limit eventually is going to be 0. Because, you know, what if this was 1 plus a to the 20? Are you going to use L'Hopital's rule 20 times? No. That's still, I mean, if you want, you can do it, but the point is that the top is a polynomial, the bottom is exponential, this grows faster. Eventually, this is going to win over this. You differentiate 20 times, the top will be a number, the bottom will still be an exponential, right? And at that point, you win. So, should know that, okay? So, this is 0 because e to the a grows faster than 1 plus a, and therefore this is 1 minus 0, which is 1. So, converges or diverges? The integral. So it converges to 1. Okay, questions? Questions?
I'm gonna ask him, how did you get the 1 minus 1 plus a over e to the a?
Okay, so how much is this?
That is 1.
Okay, so that's the same as this one over here. I just flip it.
Oh, okay.
You see, because you have a minus here. I just didn't like that minus in front, so I just wrote it as 1 minus.
Okay.
Right? It's like having negative 2 plus 3. Well, I would rather have 3 minus 2.
And then since
That's what it is.
e, you're multiplying it by something.
And then the e to a negative a, I can write it as e to the a in the denominator.
Oh, okay.
Right?
I get it.
Remember, you can change the sign of the exponent and you bring stuff from the top down or from the bottom to the top. Typically, you bring stuff from the bottom to the top, but you can also take something in the top and bring it down to the bottom, right?
X to the negative 1 is just 1, right?
Exactly. Okay? Questions? No? All right, so let's see. About, let's see, number 4. It's worth doing. I wanna have time to do number 5. So let me do number 5 before I do number. Actually, let's do number 4. I mean, we better get something that diverges. We haven't done anything that diverges. So number 4 has a. I think it's going to. It looks like it will diverge. Actually, it will diverge. So let's do number 4. Okay. So this is type 2. Yes. What is the problem?
That's 0.
It's 0. So we need to split. From 0 to 2 of 1 over x cubed dx. Okay, so we need to analyze these guys. So I1, then I2. I'm gonna work with I2 now, just to save time. But you know, you work with whichever you want at the beginning. Okay. So I2 is the integral from 0 to 2 of 1 over x cubed dx. Who can tell me what should I write here?
Limit
Mm-hmm.
as a approaches 0 of the integral of 1 over 2 dx.
What else? There's several stuff missing here.
Oh, the limits would be from a to 2.
And the limit?
From the right.
Remember, this has side limits. You need to use side limits. Which one is it, right or left? From the right. Remember, just focus on the interval, right? So because this is your lower limit, you get close to it from the right. Okay? So if it kind of confuses you, you know, just draw a little picture. 0 to 2, you're placing your A here, and you need to get towards 0. So you're doing it from the right. Okay? All right, so let's do it. Okay, I'm gonna rewrite this as x to the negative 3, just to save time. So as limit as a approaches 0 from the right of x to the negative 2 over negative 2 from a to 2. So as the limit as a approaches 0, and what is this? That will be negative 1/2 times, now that's 1 over x squared, so that's 1 over a squared minus 1 over 4. Right? Okay, so what happens to this limit? So when a approaches 0, what happens to 1 over a squared? Approaches infinity. So remember, when you have a fraction, if the top is constant and the bottom gets smaller and smaller and smaller towards 0, your fraction gets bigger and bigger. So this one goes to positive infinity. So this parenthesis is positive infinity, but because we have a negative 1/2, what is the value of this limit? Negative infinity. So this piece here goes to positive infinity, but then when you multiply by negative 1/2, the whole thing goes to actually negative infinity. Does that make sense? Okay, so there is no need to investigate anymore. One of the two integrals we obtain negative infinity, that means this limit does not exist. So the integral diverges. Because this little integral diverges, then the big one also diverges. No need to even look at I1. Okay, you don't have to look at the first integral. Remember, for the original integral to converge, both must converge. If one of them diverges, you stop right there and you say it diverges.
So would we only be asked to find whether it converges or diverges?
If it converges, you find the value.
Right.
You know, the question is to evaluate. If it converges, then you tell me, okay, what is it equal to?
Okay, so then
If it diverges, you say diverges, and you stop right there.
Okay.
Now, in next class, we're going to learn more techniques because sometimes the integrals are very difficult or impossible to compute. But you would like to be able to say whether it converges or not. So we're going to learn some techniques that will allow you to determine this, even if you cannot actually calculate it. But at least it's good to know that there is something to be found. So then you will approximate and stuff like that. Okay? So it diverges. You okay? Then for the last one, let's do number 5. And 1 over square root of x times x plus 1. This is type 1, right? Well, actually, it's type 1 and type 2. Remember, this is the one that has 2 types. So what should we do?
Split it
Why?
because it's both types.
Okay, yes, but
You need two things.
remember, the thing is that we always want to deal with one problem at a time. Okay, you don't want to, because you know, what limit do we take here? The infinity limit or the 0 limit? You know, which one do we take? So we want to have one problem at a time. So let's split this integral so we have one issue. So we can split this in such a way that one piece will be a type 1, another piece will be a type 2, right? So in this case, because the problem is a 0, and the other problem is infinity, so just pick any number you want between 0 and infinity, and split the integral like so. I'm going to choose 1, because why should I choose another number? That's not 1, right? Because 1 is very comfortable to plug in when you calculate. So, but you can pick whichever is your favorite number. So I'm going to split this as the integral from 0 to 1 plus the integral from 1 to infinity. So by doing this, I get two integers now, I1 and I2. But now this I1 is of type, what's the type of I1? Type 2. I should have called them the other way. And what's the type of I2? It's type 1. Okay? But now we know how to deal with each of these. Okay? So, let's go ahead and let's find the antiderivative and then we finish the problem. So, let's see. Because we will need it for both of them anyways. And this is also a nice little integral, so it's good too. That's why I put it there. So how do we solve this? How do we find this antiderivative? Any ideas?
We put square root of x as u.
Okay, good.
U squared,
Okay.
and then that would make dx equal to.
So very good, very good. That's the key. So let me just do it. So if you let u be equal square root of x, then what's du? Du is going to be, remember, what's the derivative of square root of x? That's 1 over 2 square root. So remember, that one appeared a lot of time called 1. So at some point you memorize it. But if you don't remember, just rewrite it as x to the 1/2, and then bring down the exponent, subtract 1, and all of that business. But the point is that it's gonna be 1 over 2 square root of x dx. Now notice that I do have a 1 over square root of x dx in here, right? So there is no need to stress over this. Just gonna move the 2 over. So 2 du is 1 over square root of x dx. Now this tells me that x equals u squared, right? If x is square root of x, that means that if u is square root of x, then x is u squared. So we are ready to make a substitution. So this becomes the integral of 1 over, now x plus 1 becomes u squared plus 1, and then dx over square root is 2 du. And this is just 2 times inverse tangent. So we get 2 times inverse tangent of square root of x. Yes? Questions? So I see don't believe nice.
Oh,
So-
just kidding, I didn't.
So 1 over square root of x dx, that's just 2 du, right? So what I put in there. And then I need to know what is x. Well, if u square root of x, x is u squared. Square in both sides. So you get u squared plus 1. That's it.
Yeah, but isn't the square root of x u?
But I already used it for my dx, right?
Oh, so you can just get rid of it and then have u.
All these, remember, all you're doing is replacing whatever has an x with u's, right? You do it however you want. I just took the advantage that 1 over square root of x dx, this part that I've highlighted here, is just the same as 2 du. Here is 2 du,
Oh, okay, no, no.
right?
Yeah.
And this, I mean, you can do this other ways. You can put a u here, then a u squared here, but then you need to compute your dx. So for dx here, that will be 2u du. This is a u. So the u up here will cancel with the u down here. At the end, you get this. I like this one. But you do it however you want.
I get it.
Okay.
Something cheap.
So that's what we get, and now you just need to take the limit. So it's just gonna be 1 minute. So let's just do it the way we finish it. So I1 was I1. So remember that was the integral from 0 to 1 of that. So that will be the limit as a approaches 0 from the right of the integral from a to 1 of this expression. So as the limit as a approaches 0 from the right of 2 inverse tangent of the square root from a to 1. That's why it's very important to use side limits, because if you do it from the left, then it's not even defined, because square root, you cannot plug in negative stuff. So as limit as a approaches 0 from the right of 2 times, okay, what's inverse tangent of 1? Okay, let me write it down. Inverse tangent of square root of 1, this is just 1, minus inverse tangent of a. So when you take the limit, what matters is the part with the a. This one is 0, of course, but what's inverse tangent of 1? It's pi over 4, right? So this is 2 times pi over 4. So it's a pi over 2, okay?
Why do you plug in, shouldn't it be square root of A? Or is it because
Yeah, square root of a. Yeah. But yes, that still goes to 0 anyways. Right? You get pi over 2. And then for the second integral, it was the integral from 1 to infinity. So this will be the limit as b approaches infinity of the integral from 1 to b. So as limit as b approaches infinity, and then 2 inverse tangent of the square root from 1 to b. And that becomes 2 times inverse tangent square root of b minus inverse tangent of 1. So we already know that's pi over 4, right? So I'm just going to write it here. And what happens to this limit? What happens to this? When b approaches infinity, the square root of infinity is just infinity. So inverse tangent of something approaching infinity, what is it? Pi over 2. So we get pi over 2 minus pi over 4. What is that? So we get 2 times pi over 2 minus pi over 4. That's 2 times pi over 4, right? But 2 times pi over 4 is pi over 2. Yes? So both integrals converge. That means the original integral converge. And what is it equal to? Pi. So there you go. Another fancy way of talking about pi. So the integral, so this would be pi over 2 plus pi over 2. So that's pi. So integral from 0 to infinity of this equals pi. So converges.